Hello friends, so today we are going to solve the questions from modern physics, and the questions are from the year 2019, total 10 questions, and all these 10 questions are from the mains, and this is part 4 for the year 2019. Okay. And first question, it states that 50 watt per meter square energy density of sunlight is normally incident on the surface of a solar panel. Some part of incident energy, 25%, is reflected from the surface and rest is absorbed. The force exerted on 1 meter square surface area will be close to. So in this case, we are given that 50 watt per meter square is intensity, energy intensity is incident, and 25% is reflected and rest is our absorbed. So we can say that our energy density suppose that is given as I, which is incident is our 50 watt per meter square, and the amount reflected is 25%. So we can see reflection is our 25%, and from here we can find out the reflected intensity. Reflected intensity, that will be equal to our 0.25 times I. So obviously the absorbed will be our 75%, or we can directly find out the absorbed intensity will be equal to 0.75 times I. So you can say absorbed intensity will be equal to 0.75 times I. Area is given to us as 1 meter square, and speed of light we already know. So first of all, we are going to find out, we need to find out the force, and so in order to find out the force, we are going to first of all find out the radiation pressure. So we can say radiation pressure. Let us suppose that it is represented as P, and we can write the formula for P. This P will be equal to 1 upon C, and we have absorbed intensity, and plus 2 times reflected intensity. We know both these values, so we can substitute them, and we get 1 upon C. Observed is our 0.75 times I, plus reflected is our 0.25 I. This comes as 1.25 I divided by C. Now we can just easily calculate the force. So we can say our force, that is our F, will be equal to pressure multiplied by our area, and pressure we just found out, that is P, is our 1.25 I divided by C multiplied by area, and area is our 1 meter square multiplied by our A. Now we can just substitute the values. So this gives us 1.25 multiplied by 50 divided by speed of light 3 into 10 to the power 8, and area is about 1 meter square. So from here we get that the force is approximately equal to 20.8 into 10 to the power minus 8 newtons. So we can say option A is correct. Option A is correct. Next question. It states that the magnetic field of an electromagnetic wave is given by this equation. The associated electric field will be. Okay, so based on this we are going to find out, magnetic field is given, we are going to find out our, you can say, the electric field. So we can say, or rather we can say, we can write the formula that the corresponding electric field let us suppose that is given as our E, then this E will be equal to C multiplied by magnetic field and cross product with K, where this K is the direction of the propagation of the wave, where this K unit vector, it is our direction of propagation of wave. Direction of propagation of wave, and value of our B naught, one second, yeah, so we can say that from the given equation, we can write that value of our B naught will be equal to 2I plus J, and speed of light we already know, that C is equal to 3 into 10 to the power 8 meter per second, and it is given, or from the question we can easily understand that the magnetic the wave is propagating along Z direction. Okay. So we can say that wave is propagating in the z direction as, or we can say since, the phase is plus k times z, which implies backward propagation. Backward propagation. Therefore, we can say thus our electric field will be equal to minus C, our magnetic field, and we have this across Z unit vector. So let us now calculate our electric field. Compute the electric field. For that, first of all, we are going to find out our B naught cross our Z. This comes as our 2I plus j unit vector cross k, and we get that our B naught will be equal to, first will be this I cross k, which will be our minus of j, and then it will be j cross k, which will be equal to our I. So we get this as minus 2j and plus I. Now we are going to multiply it by our minus of C, and let me write this as E naught, and this will be our B naught. Therefore we can say our E naught is equal to our minus of C, and we get this as minus of 2j plus I unit vector, and if you multiply by the minus sign, and one second, I forgot to mention, forgot to put the vectored notation, okay, and here also, rest is okay. So we get this as C will be equal to 2j minus of I, or we can say our E naught is equal to C times our B naught. So this comes as our 3 multiplied by 10 raised to power 8, and our B naught is given to us as 1.6 into 10 raised to power minus 6. So we get this as 1.6 into 10 raised to power minus 6, and this will be giving us 480 volt per meter. So based on this, we can write the equation for electric field. So this case of electric field will be equal to our E naught, that is our 480, and cos of this comes as our 2 into 10 to the power 7z, 2 into 10 to the power 7z plus 6 into 10 to the power 15t, and we found this is our 2j minus I, minus of I. So this is the equation of our magnetic field. So here we have to take care of one thing, that this component will be representation of our direction, which we are going to append as a vector notation, and this will be our representation of our magnetic field. So therefore we get our answer. Okay, it is written in 4.8 into 10 is power 2, so we can just write it same. That is not going to affect anything. So this will be 4 into 8 into the 10 to the power 2. So we get here, we have our minus of I and plus of 2G. So option D is correct. Option D is correct. Next question. It states that a nucleus A with a finite de Broglie wavelength lambda A undergoes spontaneous fission into two nuclei B and C of equal masses. B flies in the same direction as that of A, while C flies in the opposite direction with a velocity equal to half of that of B. The de Broglie wavelength lambda B and lambda C of B and C respectively will be. So we are given that we are having a nucleus A, and it, suppose moving in this direction, it breaks into two components. One is our B, whose direction is same as that of our A, and other one is a C, which moves in the opposite direction, and the velocity is half that of B. Okay. So let us assume that, and the mass of A and B are equal. So we can say that the de Broglie wavelength of B is, suppose, our lambda B, for C is our lambda C, and of A is our lambda A. And the standard relationship we already know, that the de Broglie wavelength that is our lambda is equal to h upon p, or we can say h upon mass into velocity. So let us assume that we are going to use conservation of momentum, and conservation of momentum. So we say that the mass of A is, let us suppose, is capital M, and it is given that mass of B is equal to mass of C, let us suppose that is equal to small m. So from here we can write that our capital M will be equal to our twice m. So we can write that our capital M is equal to twice of m. Secondly, let us assume that the velocity of A is our VA and velocity of B is our V. and in the question it is given that the velocity of C is half that of velocity of B. So we can say that velocity of C is equal to V upon 2, and it goes in the opposite direction, so sign will be a negative. Now we can just use the conservation of momentum, and we can write the equation that our mass into velocity of A will be equal to our mv plus mass into velocity of C, and m in terms of 2m, so we can write this will be equal to over 2m times VA is equal to, we can take m as common, so this becomes V minus V by 2. Here m and m cancels out, therefore we get that our VA is equal to, this becomes V by 2 and it will be our V by 4. Or from here we can say that the velocity of our B will be equal to 4 times velocity of A, and for the sake, let us say this is our VB, which is equal to V, and this is our VC. So we get our VB is equal to 4 times velocity of A, and we get our VC is equal to minus 2 times velocity of A. Now we can use the wavelength momentum relationship. Therefore we can write that our lambda A will be equal to h upon mass of A, velocity of A, and mass of A in terms of small 2m will be equal to velocity of A. Lambda of B will be equal to h upon mass times velocity of B, which comes as our h upon, this is our 4 times mVA. Similarly, finally we can write wavelength of a C is equal to, this is h upon m times VC, and this will be equal to h upon 2m times VA. Therefore we can write that our lambda B will be equal to 1 by 2 times lambda A, and lambda C is equal to our lambda A. So we get this as half and lambda A. So option B is correct. B is correct. Next question. It states that a plane electromagnetic wave traveling in a free space along x direction, the electric field component of the wave at a particular point of free space and time is E is equal to 6 volt per meter along y direction. Its corresponding magnetic field component B would be, and we are given that our magnetic field is traveling in x direction. So you can say our plane EM wave is traveling along x direction, and the electric field component is along y direction. Electric field component is in y direction, and we need to find out the magnetic field and its, you can say, direction. And we know that our electromagnetic wave, in a plane wave, the electric field is perpendicular to magnetic field, and that is perpendicular to the direction of propagation. So we can write that in free space, electric field perpendicular to magnetic field and is perpendicular to our k vector. And in this direction, we can in this question we can say if this k vector is in x direction and our electric field is in y direction, therefore we can say that then magnetic field is in z direction. And in order to find out the magnitude, we can say the magnitude of our magnetic field, that is B, is equal to E upon C, and E is already given to us, is 6 volt per meter. C we know is 3 into 10 to the power 8. This comes as 2 into 10 to the power minus 8 Tesla. So we are having magnitude as 2 and direction is our z. So option number A is correct. A is correct. Next question. It states that in a Frank Hertz experiment, an electron of energy 5.6 electron volt passes through a mercury vapor and emerges with energy of 0.7 electron volt. The minimum wavelength of photons emitted by the mercury atom is close to. So in this case, we can draw an approximate figure for that. We have electron and it passes through a mercury vapor. Suppose this is our mercury vapor, and it comes out from this mercury vapor, and energy of, you can say, its final energy when it comes out from the mercury vapor, then let us call this EF is 0.7, and before entering its energy, let us call this initial energy, and that is our 5.6. So it means the difference between our EF and EI will be the amount of energy that will be absorbed by the mercury, or we can say basically the energy loss. Therefore, we can say that our initial energy EI is our 5.6 electron volt, and we have a final energy that is our EF is 0.7 electron volt. Therefore, energy loss let us call this a delta E will be equal to 5.6 minus 0.7, giving us 4.9 electron volt. And this lost energy is, you can say, it corresponds to the excitation of the mercury atom, okay, which is re-emitted as a photon. You can say this lost energy corresponds to the excitation energy of the mercury atom, which is re-emitted as a photon. So we can use energy wavelength relationship. Energy wavelength relation, which gives us that our E is equal to hc upon lambda. From here we can write that our lambda will be equal to hc upon E, and we already know all the values. We substitute them. H is our 6.6 into 10 to the power minus 34. C is the speed of light, 3 into 10 to the power 8, and energy we calculated is 4.9 into 1.6 into 10 to the power minus 19. So this comes approximately equal to 253.2 nanometers. And we can say option A is correct. A is correct. Next question. It states that a 27 milliwatt laser beam has a cross-sectional area 10 millimeter square. The magnitude of the maximum electric field in the electromagnetic wave is given by. So here we are given the laser power is given to us and its cross-sectional area is given. Okay, so first of all we are going to find out intensity, and from that intensity we can, you can say, use the relationship between the maximum electric field and intensity, giving us the value of the electric field or maximum electric field. Okay. So we are given laser power which is our P is equal to 27 into 10 to the power minus 3 watt. Cross-sectional area is also given to us. which is A is equal to, it is given as 10 millimeter square. So we can, this is 10 into 10 to the power minus 6 meter square. And first of all, we are going to find out intensity of the wave. Intensity of wave, that is of I, is equal to power per unit area. Power is our 27 into 10 to the power minus 3. Area is 10 into 10 to the power minus 6. This gives us that our intensity is equal to 2700 watt per meter square. Now we can use relationship between intensity and maximum electric field. So we can say relation between intensity and maximum electric field, and that relationship is our I is equal to half epsilon naught C times our E naught square. And from here we can say our E naught is equal to twice I divided by epsilon naught times C and its square root. Now we simply substitute their values. We get our E naught is equal to, we have 2 into 2700 and epsilon naught is our 8.85 into 10 to the power minus 12. C is our 3 into 10 to the power 8 square root. So this gives us that the value of E naught is approximately equal to 1.427 into 10 to the power 3 volt per meter. Okay, it is a kilovolt, so we can write this as our E naught is equal to 1.42 kilovolt per meter. So option D is correct. D is correct. Next question. It states that an electromagnetic wave of intensity 50 watt per meter square enters in a medium of refractive index n without any loss. The ratio of magnitude of electric fields and the ratio of the magnitude of the magnetic fields of the wave before and after entering the medium are respectively given by. So we have to find out the ratio before and after, and we have to remember that the medium is lossless. So we can say our EM wave, it enters the medium which is a lossless medium. And whose refractive index is said to be given as n. And we have to find that the ratio of our electric field after and before and magnetic field after to magnetic field before. This ratio we are supposed to find out. So here we can just use the relationship of electric field to our intensity relationship. So we can say our electric field ratio so we are going to use the intensity relation, which gives us intensity relation. We can just, because we need to find out the ratio, we can just take in terms of the proportionality. So we can say our I is proportional to our permittivity, velocity, and multiply by our E square. So from here we can write that our electric field is proportional to 1 upon square root of permittivity times the velocity. And this can be further written as, using the relationship between the refractive index and velocity, we can say that our electric field is proportional to 1 upon, this comes as our one second, let me check. Let me do it in other way. This won't help much. So we can say, or we already know the relationship, that our velocity of light, that is c, is equal to 1 upon square root of mu naught times E naught, and the velocity v can be also written as 1 upon square root of k, and this comes as our epsilon naught times our mu naught. And if we find out the ratio of velocity of light to velocity of light in a medium, so from here we get that c upon v will be equal to square root of k, and this ratio is also equal to our refractive index. Now we can use the intensity relationship. It will be much more helpful. So we can write that, okay, intensity relationship so we can write it as, because intensity before and after, that can be written as 1 upon 2 epsilon naught E naught squared multiplied by c, and that will be equal to our 1/2, and this comes over k epsilon naught E squared times v, and this gives us half epsilon naught cancels out, so we get, and yes, so we get this as a epsilon naught square c is equal to E square upon v, and this is our multiply by k. Now let's find out the ratio. we get our E naught square upon E naught, sorry, not E naught but upon E will be equal to, this comes as our KV divided by C, and our K is, from here we can say that our K is equal to our N square. Therefore we can write this as our N square, and V upon C is equal to 1 by N. So this comes as 1 upon N, which gives us, the square goes by N, giving us this as N. Therefore E naught upon E is equal to square root of N. Or we can say that electric field after before is our square root of N. Similarly, we can write in terms of our magnetic field also. So we can say similarly we can write our, this is our magnetic field, so it comes as B naught square C divided by 2 mu naught is equal to B square V divided by twice mu naught. And this twice mu naught cancels out. So from here we get our B naught upon B is equal to V upon C. This is our square. V upon C is equal to 1 upon N. So this gives us our B naught upon B is equal to 1 upon square root of N. So we get that our option 1 upon N, yeah, option number D is correct. D is correct. Next question. It states that the electric field of a plane polarized EM wave in a free space at time t is equal to 0 is given by the expression. This is the expression of the electric field at t is equal to 0. The magnetic field B, which is represented as xzt, is given by where c is the velocity of light. So we have to find out the expression for the magnetic field. And so we can write our magnetic field, electric field. So our equation for electric field is our x comma y and time t is equal to 0 is equal to 10, and this is our cos of 6x plus 8z, and this is our j unit vector. So this is the direction and this is representation of our magnitude. And the general form for our EM wave, that's the basic concept, we can say the general form of EM wave, we know that our electric field is perpendicular to the magnetic field and is perpendicular to our k vector, and we can also say that our k dot E will be equal to our 0, and we can also say that our k dot B will be also equal to 0, and we can write that our cross product of electric field, its result will be parallel to our parallel to our k vector. And in respect to magnitude, we can write that the magnetic field magnitude is equal to electric field magnitude divided by c. So this is the basic this. And here we have to remember k is the representation of the wave vector, not the unit vector. So let's first of all find out what will be this k vector. Sorry, not k vector but wave vector. So we can say our wave vector k, and the phase of the given wave is given to us, that is our phi is equal to 6x plus 8z. Therefore, we can write our wave vector k will be equal to 6i plus 8 k unit vector, and which from here we can also say that the wave propagates in direction that is our wave vector k, which is given as 6i plus 8 k unit vector. Now we can write that the given equation for our electric field, from where we are going to find out its direction. So we are given that electric field is our 10 cos of 6x plus 8z, and in terms of time we can write it, there is no harm in writing this, because this time t is equal to 0 and it will be coming back to the same formation. And from here we can say that the direction of electric field is along j unit vector, or we can say along y axis, Now we can easily find out the b vector. We can say our b vector will be equal to 1 upon c, and we have this as our k unit vector cross electric field, and we know that the direction of propagation, that is our wave vector, that is our k vector, is our 6i plus 8k, and from here we can find out the k unit vector. Therefore, we can say the k unit vector, or we can also call it as a normalization. Let me write. So you can say through normalization we get our k unit vector is equal to 6i plus 8k and divided by 6 square plus 8 square, and we get k unit vector will be equal to 6I plus 8k and divided by 10. Now we can easily find out our magnetic field by using the same formula. So we can say our magnetic field is our 1 upon c, and this comes as 6I plus 8k divided by 10. Cross product, and electric field equation is our 10 cos of 6x plus 8z minus omega t times j. And we get this will be our one second. Okay, so we need to find out the cross product of I as well as our this 6I plus 8k. So let me write it separately. So we have 6I plus 8k and cross product j, which gives us 6k minus 8I. Therefore, we can write our magnetic field B is equal to 1 upon c times 1 upon 10, and this gives us our 10 cos of 6x plus 8z minus omega t and multiply by 6k unit vector minus 8I unit vector. And here 10 cancels out with 10, so we get our magnetic field B is equal to, in what format it is written, okay, let me write in the same. So directional vector is 1 upon c times 6k minus 8I cos of 6x plus 8z minus omega t, and we are going to find out our, one second, yeah, we are going to find out our omega. Okay. And we know that our omega is equal to our c, and we have this as k unit vector, that is a wave vector, its magnitude. So we can write this as 3 into 10 to the power 8 square root of, this comes as our 6 square plus 8 square, and this will be our 10. So we get this as 3 into 10 to the power 8 multiplied by 10. Or we can keep it as c, so we can say our omega is equal to 10 times c. So this will be giving us a final answer that our magnetic field B is equal to 1 upon c 6k unit vector minus 8I cos of 6x plus 8z minus 10c t. So this is our magnetic field. So the option that is our 6 minus 10, 6 minus 8 and minus of 10. So option B is correct. B is correct. Next question. It is given that if the magnetic field of a plane EM wave is given by this equation, then the maximum electric field associated with it is. So the basic formula is, we know that our relationship between maximum electric field and magnetic field. Okay, so we can write that our maximum electric field let us suppose that is given as Emax, and we have maximum magnetic field let us suppose that is our Bmax, and their relationship will be our Emax is equal to C times Bmax, and magnetic field is given to us, so this is our Bmax. So from equation we can say that our Bmax is equal to 100 into 10 to the power minus 6, or we can say it is equal to 1 into 10 to the power minus 4 Tesla. So simply multiply it by C, we get our Emax. So we get our Emax is equal to 3 into 10 to the power 8 multiplied by 1 into 10 to the power minus 4. This gives us 3 into 10 to the power 4 volt per meters. So option number C is correct. Is correct. Next question. It states that in an electron microscope, the resolution that can be achieved is of the order of the wavelength of electrons used. To resolve a width of 7.5 into 10 to the power minus 12 meter, the minimum electron energy required is close to. So it says that resolution is in the order of the wavelength, and the width that to be resolved is 7.5 into 10 to the power minus 12. Therefore, we can write that the wavelength lambda will be equal to 7.5 into 10 to the power minus 12 meters. Now we have to find out the energy. We can use the relationship between our, you can say, de Broglie wavelength, and that will be giving us the relationship. So we can say de Broglie wavelength that is our lambda is equal to h upon our p, that is our momentum. And we already know the relationship with momentum and energy. We can say our momentum p will be equal to twice mass of electron multiplied by energy and its square root. And this energy is in terms of our joules. Therefore, we can write that our lambda is equal to h upon twice me and its square root. Therefore, our energy E is equal to h square upon 2 mass of electron and its square. And we already know the values, we substitute them. We get this as 6.6 into 10 to the power minus 34 whole square. 2 times mass of electron is 9.11 into 10 to the power minus 31, and the wavelength is our 7.5 into 10 to the power minus 12 and whole square. So we get our electric field, energy E is equal to approximately, this will be coming as 4.28 into 10 to the power minus 15 joules. So this is electron volt. So we can just simply divide it by 1.6 10 to the power minus 19, and this will be coming now in electron volt. So this approximately will be equal to, electric field is approximately equal to 26.75 kilo electron volt. So option number D is correct. Option D is correct. So this completes all the 10 questions, or rather we can say part 4 for the year 2019. We have already done total parts 3 we have already completed, and all those part 3 were consisting of only 2019 mains question. So part 4 is also for the 2019 mains question, consisting of, this part is of 10 questions. So this completes all the 10 questions for the year 2019. Thank you.